Hello everyone. Today we'll learn about lasers, the introduction to lasers, the processes which are involved when light interacts with matter, or specifically what is stimulated emission, induced absorption and spontaneous emission, followed by the relation between Einstein coefficients A and B. Introduction. What is the full form of lasers? Laser stands for light amplification by stimulated emission of radiation. Working principle of the laser is it works on the principle of stimulated emission of radiation. And why lasers are so popular? I should say lasers are one of the revolution in the field of science, and experimental fields have flourished a lot, all due to lasers. Now, characteristics of lasers. I am also adding very few formulae which will be useful to you all. So first characteristics is lasers are highly coherent in nature. So we already know what is coherence. So a very simple formula is coherent length L is equal to coherence time T into velocity of light in free space, that is small c. Second characteristic is lasers are highly directional in nature. Directional means we see a very single small spot on the wall when we flash laser onto the wall. So that means the laser beam is highly concentrated, highly directional in nature. So divergence of laser beam is of the order of 10 to the power minus 5 radians. That is very small. Next one is highly intense. Why? Because we get a lot of coherent photons here. So the beam is very intense. The number of photons emitted by a laser per second is equal to power of laser by energy of one photon, that is h nu. So when we purchase any laser in the market, so you will see that we purchase it uh, seeing the power output of the laser, say in 25 milliwatts or so. So we know the power of the laser when we purchase it, and we also know what is the wavelength of the laser. Say it is red color or blue color. So that is how we purchase the laser. So we know the lambda value. We also can calculate what is h nu then. Nu is the frequency. So next is lasers are highly monochromatic in nature. Highly monochromatic in nature means the laser beam, if it is for say 650 nanometers, then there will be a very less expansion around 650 nanometers. Say it will be something like 640 to 660 nanometers. So there will be the highest intensity of the laser found. So that is why these are highly monochromatic in nature. We also have a formula called degree of non-monochromaticity, which is given as epsilon, which is equal to bandwidth of the laser, that is given by delta mu by central frequency of the laser nu naught. So central frequency can be calculated from the wavelength of the laser. Also bandwidth of the laser is equal to 1 by coherence time. So bandwidth units are in hertz. Next, now interaction of light with matter. Now what happens when light interacts with matter? Because this is very important to understand the working principle of lasers, and that is where we start with. So three quantum processes take place in a medium when light interacts with it. In these processes, two energy levels of atoms are involved. So let us say E1 and E2 be the ground and excited states of an atom. Transition between these states involves absorption or emission of a photon of energy E2 minus E1 equal to h nu, where h is called the Planck's constant and nu is the frequency. So in the diagram you can see here we have two energy states E1 and E2. E2 is greater than E1, and h nu is the energy of the photon incident onto this system, and h nu is equal to E2 minus E1. So U nu is here the energy density of the incident photon. So let me start with the first process, which is called induced absorption or stimulated absorption. If a photon of energy h nu which is E2 minus E1, and energy density U nu collides with an atom present in the ground state of energy E1, then atom completely absorbs the incident photon. The atom is here in energy state E1, that is the stable state for the atom, absorbs the incident photon and makes transition to excited state E2. Now, when we talk about the transition had been made, the atom has absorbed the energy and it goes to the higher energy state, it gets excited to energy state E2, then we are talking about transition probability. There will be a probability associated to this transition. What is the probability? The notation for this probability, we'll be using this formula shortly. The notation for this probability will be P12 because the transition is taking place from 1 to 2, energy level 1 to 2. So that is equal to B12 U nu, or we can say P12 is proportional to U nu, the energy density. The more the energy density, the more the transition probability for induced absorption process. So what is B12? It is known as Einstein coefficient of induced absorption. So we'll go to the next process, that is called spontaneous emission. Now, once the atom is in the higher energy state, the atom falls down to the ground state on its own because it is unstable at the excited state. So this transition occurs in around 10 to the power minus 8 seconds. An atom initially present in the excited state makes transition voluntarily on its own to the ground state, emitting a photon of energy h nu E2 minus E1. So it falls down to the ground state, releasing a photon which is incoherent photon and which is in any direction possible. So it can be in any direction. These photons are incoherent in nature. Example, the glowing tube light, candle flame, etc. Now, because the photon is emitted without any external stimuli, so that means the probability, now this is the probability for this process, P21 spontaneous, SPON, is equal to some constant value A21, which is called the Einstein coefficient for spontaneous emission. So you see here there is no concept of U nu because it is falling on its own in around 10 to the power minus 8 seconds. We go to the third and most important process, which is the heart of the lasers, that is called stimulated emission process. Now what happens in stimulated emission process is a photon having energy h nu, that is E2 minus E1, impinges on an atom present in the excited state. Now again, when the atom is present in the excited state, it gets some energy h nu with the energy density U nu, and it stimulates it to make a transition to the ground state, giving off a photon of energy h nu. The emitted photon is in phase with the incident photon and hence are said to be coherent in nature. So if you see here, this photon which impinges on the atom in the excited state now forces this atom to fall down and release the photon in the same direction as of the incident photon, or both are said to be perfectly coherent with each other. Now the transition probability for this emission process is P21 because transition is taking place from second to first energy state. So P21 is proportional to U nu again, and B21 is called the Einstein coefficient of stimulated emission. So the P21 stimulated is B21 U nu. So this is very important process. You see here, you see an photon amplification. One photon is impinging and you get two photons here. So this is the heart of lasers. Now, once we know what these coefficients are, Einstein coefficients, we need to find how they are helping me to understand laser action, and let us find some relations between these Einstein coefficients, and this is a very important derivation to understand the working of lasers also. So let us start with the derivation. Let N1 and N2 be the number of atoms in energy states 1 and 2. The atoms in energy state 1, that is E1, can absorb photons and give rise to absorption per unit time, given as N1P12 is equal to N1B12 U nu. Now P12 is the induced absorption probability we have studied just now. So we just substitute that value here. What we are doing here is we are finding the number of atoms which will undergo induced absorption will be N1, which is the population of that particular level 1 times the probability. Now the atoms in energy state E2 can return to energy state E1 through two processes of emission, which can be spontaneous and stimulated both. This emission per unit time can be given as follows. So we have to add the probabilities of both the emissions. So N2P21 is equal to N2 times A21 plus B21 U nu. These are the probabilities of spontaneous and stimulated emissions. So these have been added here. Now in thermal equilibrium, both the rates of absorption and emission will be same. So we equate these two probabilities. N1P12 is equal to N2P21 or N1B12 U nu is equal to N2A21 plus B21 U nu. So we rearrange and we get energy density U nu to be A21 by B21 times 1 by N1 by N2 times B12 by B21 minus 1. Now we have to substitute for N1 by N2. So we use the Boltzmann Distribution Law. The number of atoms N1 and N2 in energy states E1 and E2 in thermal equilibrium at temperature T are given as follows. So N1 is equal to N0 times e to the power minus E1 by Kt. The K is the Boltzmann constant and N0 is the ground state number of atoms. And N2 is equal to N0 times e to the power minus E1 by Kt. If we divide these, we get N2 by N1, which is e to the power minus E2 minus E1 by Kt, which implies N1 by N2 is equal to e to the power h nu by Kt, where I have used E2 minus E1 is equal to h nu. So we have this value, we'll substitute back in the equation of energy density. So hence we get U nu is equal to A21 by B21 into 1 by e to the power h nu by Kt, B12 by B21 minus 1. Now comparing the above equation with the Planck's radiation law, which is U nu is equal to 8 pi h nu cube by c cube times 1 by e to the power h nu by Kt minus 1. Why do we compare this equation here with Planck's radiation law? Because laser can be considered as a black body radiator. So we can compare the law for the black body to be similar with the energy density we have obtained for our system here. So we, after comparing, we can get the relations between Einstein coefficients. You see here, this 8 pi h nu cube by c cube becomes equal to A21 by B21 here, which implies A21 by B21 is proportional to nu cube. And this value B12 by B21 is equal to 1 here. So B12 is equal to B21. So what we understand is this relation shows that the probability of spontaneous emission dominates over induced or stimulated emission. Also, the ratio of spontaneous to stimulated emission is proportional to the frequency of radiations. So these are very important relations if you want to understand the working of lasers. Thank you.